Every day, millions of people rely on pharmaceutical drugs. But what happens when these compounds enter our water systems? Pharmaceutical waste is a growing environmental concern. These compounds are non-biodegradable, meaning they persist in water sources for years, contaminating ecosystems and even drinking water supplies. Traditional wastewater treatment methods fail to remove these pollutants effectively. Conventional techniques lack efficiency, allowing harmful residues to accumulate and impact aquatic life and human health. One common solution is activated carbon, widely used for water purification. However, activated carbon is non-renewable, requiring high energy for production and leading to sustainability challenges. A better eco-friendly solution is needed. How can we develop a more effective and sustainable method to remove pharmaceutical pollutants? Water pollution is a growing crisis, and one major contributor to this problem is pharmaceutical waste. But how can we effectively remove these contaminants? One promising solution is adsorption. Adsorption is a surface-based process in which the molecules attach themselves to a solid material, making it an efficient method for water treatment. Due to its simplicity, efficiency across various pH levels, and environmentally friendly nature, adsorption is widely used for water treatment. In this study, we will focus on industries that sell water in rural areas instead of a direct household consumption. This is because these industries often struggle with pharmaceutical wastes, which are often more difficult to remove through conventional water treatment methods. Our primary concern is pharmaceutical waste, specifically chloramphenicol and acetaminophen. These substances are often used in the medical and pharmaceutical industries, but 58 to 68% of these substances are often discharged into the environment, posing serious health risks. Chloramphenicol, for example, is often associated with aplastic anemia, leukopenia, and neutropenia, while acetaminophen can lead to contamination, which affects liver toxicity as well as environmental persistence. By developing an efficient adsorption-based treatment system, we aim to reduce pharmaceutical pollution as well as provide a safer water supply in rural areas. Our research focuses on developing an activated carbon absorbent from corn cob in order to remove pharmaceutical compounds from water. So, let's see how we produce those activated carbon absorbent from corn cob. The first stage is the carbonization of corn cob, CC. The raw corn cob is heated in a vertical furnace at 550 degrees Celsius under a nitrogen flow of 150 millimeters per minute. This process converts the biomass into char, a carbon-rich material with high adsorption potential. The next stage is the impregnation of char. The char is then impregnated with potassium hydroxide, where we carefully adjust the impregnation ratio to enhance porosity and absorption efficiency. The next key stage is microwave activation. The impregnated char will undergo microwave activation under a CO2 flow of 150 mm per minute. By manipulating the activation time and radiation power, we further improve the adsorbent's surface area and functionality. Another key stage to this process is characterization studies, in which we evaluate the material's properties by performing several analyses, which includes scanning electron microscopy, SEM, for surface morphology, BET surface area analysis for porosity, Fourier transform infrared spectroscopy, FTIR, for functional groups, elemental analysis, EA, and proximate analysis, PA, for composition assessment. So, let's evaluate the efficiency of our product. Can our product perform effectively in these targeted areas?
After conducting numerous tests, the graph clearly demonstrates that CCAC exhibits a high absorption capacity over time. Specifically, CCAC can absorb between 68 to 99% of ACP and CP from their initial concentrations in polluted water. Additionally, tests indicate that CCAC performs favorably in low pH conditions, which is particularly beneficial since most polluted water is highly acidic. These results confirm that CCAC is both highly effective and efficient for water treatment applications. Hence, how can we transform corn cob activated carbon into a commercially viable product? We will use a biomass crusher machine to grind activated carbon derived from corn cobs into a uniform, specific size, making it suitable for commercialization in the water treatment industry. In conclusion, our project demonstrates that a sustainable future for water treatment is within reach. By turning corn cob into activated carbon, we provide an affordable, portable and effective solution to remove harmful substances from water source. This is due to the simplicity of the tablet format, which makes clean water accessible even in remote or disaster-affected areas, empowering communities and reducing environmental impact. Lastly, this innovation highlights the potential of circular economy practices, which turning waste into valuable resource for public health and environmental sustainability.